This problem wants us to find the natural frequencies of this beam in transverse loading. So we want to find all of the omega n for this continuous beam. So first, I'm going to combine here the modeling step, the equation of motion, and the identify, since once we can identify the type of beam it is, we know all of the other aspects of it. The interesting part on this one will be applying the boundary conditions, finding those natural frequencies though. If we look at the beam, it is made of steel, so we have a constant material, which means that E and rho are constant. And also constant is going to be our cross-sectional area. So A and I are constant as well. And we have free vibration. So because all of those are satisfied and we are looking at transverse loading in this case, then this is going to let us say that the governing equation, the equation of motion, is that c squared del to the fourth w del x to the fourth plus del squared w del t squared equals 0. So for transverse loading like we have here, I guess it's not quite clear in the prompt, but this is going in a transverse direction only. That is going to be our equation of motion that we are going to be using. And we need to identify that we can use this as our equation of motion as our PDE so that we have a separable w and t as part of our full solution to w of xt, because that's how we're going to be applying our boundary conditions in order to find our eigenfunction, but more importantly for this one, in order to find our natural frequencies. But being able to identify that this is the case, constant E and rho, constant A and I, free vibration, now we can start to proceed because we care about the natural frequencies. So this means that w of xt can be written as w of x, t of t. Again, because this separable PDE applies to this transverse loading problem. So as far as our parameters, we are going to be finding our omega n. And for this problem, that's all we're going to really care about. And in order to do that, we have to apply boundary conditions. All right, so our boundary condition step. So let's take a look here at what our boundary conditions are and how it's going to relate to our w of x, which will become our eigenfunction. We have here a fixed free beam that I'm going to define, as is typical, that x is going to go from left to right. So x of 0, and it has a length of L, 2 meters. So as far as our boundary conditions go, let's look up here. Boundary conditions for these transverse problems are going to be places we know the position, where big W is 0, or we know the slope is 0, in the case here where we're looking at homogeneous boundary conditions, so W prime is 0, where the internal bending moment is 0, or where the internal shear force is 0. So bending moment is going to be our W double prime, and the shear force is going to be our W triple prime. And for statically determinate problems like we have here, we're going to have 4 of these boundary conditions. So let's start identifying them. I'll start where x is equal to 0 at the wall and see what we know there. So for this transverse problem, we are going to know that W, the position at the wall, so x equals 0, will be 0. That's our first boundary condition. We also know at the wall, going back up, the slope at the wall must be 0. Directly at the wall, it has to maintain a horizontal slope. Right, that's all we can say about the wall. The moment at the wall is not always going to be 0 at all points in time, and the shear force at the wall is not going to be 0 at all points in time. So again, these boundary conditions are true at all points in time. If we go to the free end, x equals L, well, the position there, the vertical position, is not going to be fixed at 0. The slope is not going to be fixed at 0. However, at the free end, we know that the internal bending moment must be 0 at the free end, and the internal shear force will be 0. So we can say that W double prime at L is 0, and W triple prime of L is equal to 0. So bending moment, the double prime, and internal shear force, the triple prime. And those are going to make up these 4 boundary conditions. So identifying them, important first step. W of x, our assumed solution, we are going to use this C1 cosine beta x plus C2 sine beta x plus C3 cosh, or hyperbolic cosine beta x, plus C4 sinh beta x. That's the assumed solution we get because we have this d to the 4th dx to the 4th w minus this beta to the 4th w equals 0 is the ODE for w that we get from making that separable equation. So this is the assumed solution, or the form of the solution for this 4th order type of problem. So that's where this w of x comes from. Now, if we look at our boundary conditions, we have a w prime, a w double prime, a w triple prime. So I'm going to write out explicitly all of the derivatives of w. Remember, w is now a single variable function, so I can differentiate with respect to x. So if I take w of x and I differentiate once with respect to x, what do we get? Well, we're going to have, term by term, a cosine beta x. Remember here we have to use a chain rule. So we are going to get a beta c1. Beta comes out from the chain rule, and then the derivative of cosine beta x. The derivative of cosine is going to give us negative sine. So sine beta x and a negative out in front. For the second term, again, chain rule is going to be applied. So we have a beta c2. Sine goes to positive cosine beta x. From chain rule, beta comes out in front. The derivative of cosh is positive sinh. So positive sinh beta x. And here a beta comes out, c to the 4th, sinh is going to go to cosh beta x. And I can take another derivative. Once again, another chain rule, another beta comes out in front, a beta squared c1, sine goes to cosine. Beta x, still that negative out in front. We have another beta coming out, c2, cosine goes to negative sine. Plus another beta comes out, c to the 3rd, sinh goes to cosh, no change in sign on the hyperbolic functions. Another beta comes out, c to the 4, or c4, cosh goes to sinh beta x. And then the third derivative, differentiating one more time, we are going to have another beta come out, so beta cubed c1 cosine is once again going to go to negative sine. So the negatives are going to cancel, so there's just a positive out in front. Minus another beta comes out, c2, sine goes to cosine, plus a beta 3, c3, cosh goes to sinh, a beta cubed, c4, sinh goes to cosh, beta x. So those are, in general, the spatial derivatives of w, the first, the second, the third spatial derivative of w. So how does that translate to now applying our boundary conditions? For the first boundary condition, 1, w of 0 equals 0. And if we go up to w of x and put in 0 everywhere, what do we have? We have c1 times the cosine of 0. The cosine of 0 is going to be 1, plus c2 times the sine of 0. The sine of 0 is 0, so that's going to be 0, plus c3 times the cosh of 0. Just like cosine, cosh of 0 is going to give us 1, plus c4 times the sinh of 0. Like sine, the sinh of 0 is also 0. So I'm explicitly putting in those 0 terms so that we do not forget about them. And so that's our first boundary condition. c1 plus c3 equals 0. But I'm going to leave it written in this way because we're going to be going into a matrix form. Second boundary condition, w prime of 0 is equal to 0. So we can use this w prime of x and apply 0 here. So for the first term, I have a sine of 0 is going to be 0, plus a beta c2 cosine of 0 is 1. Then my third term, sinh of 0 is 0. And then my fourth term, beta c4, cosh of 0 is 1. So I have 0 equals beta c2 plus beta c4. And what I want to do here is both terms have a beta. I can divide through by that beta because beta cannot be 0. It is going to be related to our natural frequencies, but we know it's never 0. So I can divide through by it. So I'm left with a c2 and a c4. My third boundary condition on the internal bending moment at the free end, so now I have L, is equal to 0. And what do I have in here? Applying my double prime, I will have a negative beta squared c1 cosine beta L minus beta squared c2 sine beta L plus beta squared c3 cosh beta L. And L is 2, but I'll apply that later, plus beta squared c4 sinh beta L. I have beta squareds everywhere. Those are going to drop out. And I have my fourth boundary condition. The triple prime at L is 0. So internal shear force at the free end, 0. Using my triple prime equation, beta cubed c1 sine beta L minus beta cubed c2 cosine beta L plus beta cubed c3 sinh beta L plus b cubed beta cubed c4 cosh beta L. And like the other ones, it's homogeneous. I can divide through by this beta cubed and simplify this a little bit. So I want to take these four scalar equations and rewrite them with this matrix form in mind. I want to rewrite these as some matrix A, it's going to be 4 by 4, times C is equal to 0. Because this A matrix, I need to ensure its determinant is 0 so that this equation has a non-trivial solution, which is to say that not all of the C values are 0. So I want to rewrite this. I need to make this A matrix. Looking at my first equation, I'm going to have a 1, a 0, a 1, and a 0. And if we see what's going to happen here, I'm going to be multiplying this by C1, 2, 3, 4. So I'm pulling out those constant terms, and then the right-hand side is going to be my 0 vector. My second row is my second equation, 0, and then I have 1, 0, and 1. In my third one, I'll have a negative. The C1 comes out, so cosine beta L minus a sine beta L in the second spot, a cosh beta L in the third spot, and a sinh, this was a sinh up here, beta L. And then my fourth row, fourth equation, I have a sine beta L, a negative cosine beta L, sinh beta L, and cosh beta L. So the form of the A matrix is going to be dependent on my boundary conditions. So depending on where, if I have a free end or a fixed end or a pin, will determine what this A looks like. So again, this is that A matrix here. This is my C vector equals 0. So that's the form I want to get it in after I apply these four boundary conditions. And what I want to say or enforce is that the determinant of this A matrix is 0. Now, A is a 4 by 4 matrix. I can take its determinant. Taking anything, even a 3 by 3 is sometimes a little bit daunting. A 4 by 4 is not going to be very fun. So I am going to let Mathematica do this determinant for me. It's going to take a 4x4 matrix and give me a scalar equation that I will be able to set to 0. In Mathematica, I'll recreate some of these steps I just took by hand and then get to the actual determinant of the matrix. So I can define this w of x term, again, cosine, sine, cosh, and sinh, and I can apply those boundary conditions the same way I was doing it by hand, where that beta is always going to cancel out when I have these homogeneous boundary conditions. So more importantly, this matrix, I'm calling it AB here, just so it doesn't get confused with, sometimes it doesn't like single capital letters because they're reserved. But if we see what I have here, that's exactly what I wrote on the by hand here. So I just copied it in here. I am using here a capital L just so it doesn't look like a 1. But I'm defining this AB matrix. I'm going to take its determinant, and I'm going to let Mathematica simplify it, as we're going to see what happens here when we do that simplification. So running it in Mathematica, we get that the determinant of 0, or the determinant of A, making it be equal to 0, we get this expression, which then when we let Mathematica simplify it, will simplify down. Let's take a look at what Mathematica is doing though. This step here, taking the determinant of the 4x4, this is the huge time saver Mathematica is giving us. Taking the determinant of a 4x4 matrix would have taken us a long time, but let's make sure we can get to the simplified form that it gives us. So I will transcribe what Mathematica gave us before it did the simplification automatically. So this cosine beta L squared plus 2 cosine beta L cosh beta L plus a cosh beta L squared plus a sine squared beta L minus a sinh squared beta L equals 0. So we can apply some trig substitution rules here. So first, if we see here, we have a cosine squared beta L and a sine squared beta L. This one we should remember from trigonometry that cosine squared plus sine squared, as long as they have the same argument, here they both have beta L, are going to be equal to 1. So these two we can combine, and that's going to be 1. Now, a little bit less memorable is for hyperbolic functions. We have this cosh squared beta L, and we have a negative sinh beta L. These two can combine, and it has a different rule than with the normal trig functions. A cosh squared minus a sinh squared, that is equal to positive 1. So we can rewrite this now as we have a 1 and a 1. We have a 2 plus a 2 cosine beta L cosh beta L equals 0. And the 2's can drop out. And we are going to be left with this expression for the determinant of A, that 1 plus cosine beta L cosh beta L equals 0. So that, if this is true, all the betas that make this equation true ensure the determinant of that A matrix is 0, which ensure that we don't get a trivial solution. So what we're going to do with this is we need to solve this for all of the beta, or BNs, that make that expression true. And specifically, we can put in here that L for this problem was 2 and get those solutions. If we look at the form of this, we have a cosine times a cosh. We cannot solve for beta by hand. For the values of beta here, we don't have trig rules that are going to be able to get us nice closed form solutions for beta. So if we can't get a good analytical solution, that means we are going to go with a numerical solution. I already have it set up here that the right-hand side is 0, so what we're going to be able to do is use fzero or some root finder to find all of the betas that will make this true. But we're going to see that it's not too easy to do that. We have to be a little bit tricky. Now, the first thing we're going to realize is that we only want positive values of beta for this. We're going to be squaring them, and we're going to be using them to find natural frequencies, but the smallest beta can be is a number greater than 0. For this exercise, I am only going to find the first 4 betas, which will then give the first 4 natural frequencies, but I could find as many as I want. It's just that I don't get a nice equation for them. I'm going to have to go through this process to find 4, 8, 12, however many betas I want. So I'll get to what some of these things are going to be telling us in a second. Let's first plot this function and see what we're dealing with. So remember, this is the function we want here to find the roots of, this 1 plus cosine beta L cosh beta L. And again, L is 2 in this problem, 2 meters. So our base, in base units, it's 2. So this is what the function looks like for the function and the values of beta. So what we want graphically would be, where are all the 0 crossings of this 1 plus cosine beta L cosh beta L function? What betas make this thing equal to 0? Well, we can see at least graphically 1 over here. So we should have, now we have to kind of zoom in a lot for where it actually is crossing 0. But somewhere around, if I put it in here, 3.92, somewhere like that, 3.924 is going to be one of the roots of this expression. However, and this is where trying to do it graphically is tough, there can be a lot of 0 crossings before we get to that point. And we just might have to zoom in a lot to get there. Okay, so if we zoom in fact, there is going to be one. Again, graphically, we can approximate where it is. About 0.93, somewhere in there, we have a 0 crossing. But we want to do this in a more systematic way than just trying to eyeball it from a graph. So fzero is going to help us do that. However, the tricky part is going to be, we don't know how far apart these roots are, so we don't know necessarily where to be expecting them. And we'll see in the code how we can overcome that. So what we want to do is, the way I have my root finding set up, we'll go through those steps, but I'll explain my thought process in finding this. I want to find a beta, or I'm calling it B here, that makes this expression 0. But I need to do it in kind of a particular way. So what I'm going to do is I'm using fzero here, and I'll work kind of from the inside of this first loop out so we can see how I am doing it. So this is the expression I want to find the 0 of, and I'm telling it find the beta that makes this expression 0. F0 or an fmin search, but F0 here in particular is the answer we get can be very dependent on the initial guess, or what I'm calling SP, the start point. So what I am trying to do is find, because F0 will only return a single root at a time, often the closest root to my start point, but that's not necessarily true. But I know there's an infinite number of roots to this equation. So the tricky part about this is I need to find them in order from lowest to highest. And I want to make sure that I don't lose any along the way. So this start point is really going to be a crucial factor here to making sure I am finding, as I increase my values of beta, that I haven't accidentally skipped one. So if we look now back in the code, my start point here, I'm going to start really, really small, 1 times 10 to the negative 5, so a number that's a little bit above 0. I'm going to start looking for my first beta, the first beta that makes this, that solves this root. All right, so what I'm going to do here is if I just use, so if SP here is that really small number, let me go into F0 and see what I get out. All right, so it's saying that a beta that makes this true is negative 0.937. And mathematically, yes, that is true. That is a root to this equation, but I only want positive roots, and this one's a negative one. So this is not a good root. Mathematically, yes, but in terms of what is my first beta, my first positive beta, I haven't found it, which means probably my starting point was too small. And this is kind of where the solution gravitated to. So what I'm doing in this loop is I'm going to keep checking 2 things. 1, I am going to make sure, so if we see what's coming out of this f0, I'll run this line again here. I'm getting a q value. That is my current best guess at beta, and we know that this one is bad. It's negative. I'm getting f, which is going to be the value of the function, which I'm just checking here. It should be 0 or really, really small, and here it is. So this is probably a real root. And I want to check my flag. So here I'm getting a flag of 1. A flag of 1 is an indication that it did converge to a solution. So between f being really small and a flag of 1, this means that the f0 worked, but the q value, the beta that it found, isn't good, is a problem that we have to address. And then this OOT, this OOT, is just some information. I'm not really using it for this, but I am going to save it. Okay, so the problem here is, from the first time when my starting point was this really tiny number, is that my q is negative, so that's not good, but it did converge. My flag is 1, my f is really small, close to 0. So what I'm going to do is increase the initial guess. So that's what I'm doing in 23 here, is as I go through this loop, I'm going to slowly increase my initial guess. So you see here, I'm going to multiply my current value by this 1.001, so I can kind of slowly keep increasing my guess until I get a solution that's positive. And hopefully, if I go slow enough in increasing my guess, the first positive value I find will be the first positive beta that satisfies this expression. So let's see what I'm doing. I'm going to do this in a while loop. So I'm going to be checking keep running this while either q is less than that 1 times 10 to the negative 5. So that is that initial guess here. So this is going to ensure that q, the output from this f0, or my first beta, it's ensuring that the value it finds is positive. If I find, like here, q is negative, so that's not good. So it's going to keep running because q would be less than 1 times 10 to the negative 5th on this iteration. So that tells it, run this loop again and keep running it by increasing that start point a little bit. And I put in this extra condition here, or keep running this loop if the flag I find is anything but 1, which means that the solution did not converge. All right, so we see that for a start point that I just put in there, I am not getting a q value that's good. It's not positive. Let me now run this whole while loop. Right, so it ran, and you'll notice my start point has increased from that initial 1 times 10 to the negative 5th. It cut out of the while loop when it reached 6. So if I run everything up to including this while loop to completion, let's see what it finds for that first value. Let's look in the workspace over here. So the while loop stopped, and we have found q is 0.9376. So it's actually, graphically, we thought that that was a zero crossing. This is the first root, or very likely the first root. I can't actually be sure when I'm doing this numerically, which is a little bit of a downside of this numerical solution. So I'm going to take that q and save it to B list, which will be my list of beta values. This is my first one. All right, so that's good. But now I need to find the next smallest beta value. And now finding the first one was just a little bit extra tricky because I needed to make sure it was not negative. So subsequently, in this for loop of 26, I'm going to keep finding the second, the third, the fourth, in this case, beta value, and then stop. If I want to find more than 4, I could keep this going. But the premise of finding the second, and then the third, and then the fourth will be the same. So in this next loop, this for loop, what I'm going to do, for example, when k is 2, I am now searching for the second smallest beta value. So what I'm going to do is set my start point to a little bit higher than the next lowest beta value, which when k is 2, that's going to go and refer back to that first beta value. So my starting point is going to be a little bit more than my previous beta value. Now this is going to get trickier because with this f0, I want to make sure I am not finding duplicate beta values. So let's see what happens here for k is 2. So let me just arbitrarily say k is 2 so we can see what's happening in here. All right, so my start point is a little bit larger than my first beta value. And if I go here, I'll ignore this while loop for the moment. If I run this, I get out, scrolling up, a q value. So it found a solution if the flag is positive and q is here. But I already know that root. So my start point was too close to my previous root that this solution also went back to the previous root. So I don't want to find duplicates. So what this while loop is going to do is it's checking, is this q value you found bigger than 10% different than the previous beta value? So in this case, it would not be. So let's just check because it's virtually identical. Right, so it is less than 10%. I am considering that then equal to my previous beta value. So here's the tricky part, is that because fzero is doing this numerically, I'm not going to find exactly the same root a second time. It might be the same to 8 decimal places, and then in the 9th, it's just a little bit different. So I can't be so strict to say, is this new root not equal to the previous root? Because that probably will be true, because it will be very, very slightly different. So that's why I'm putting in this little comparison here. I'm asking, is it at least 10% different than the previous root? Now, this 10% I'm picking arbitrarily. I don't want to go too small, or I'm going to get a lot of false positives. I'm going to get a lot of duplicates that are a little bit different than the previous one. But at the same time, I don't want to go too big on this value because I don't want to accidentally miss the next root in order. So if I end up coming to the same root, what I'm determining as a duplicate root, I am, like in the previous while loop here, I'm going to increase this starting point a little bit at a time. And I'm going to keep running this while loop until I have found a new, what I'm considering a new unique root. So let's run this whole thing for k is 2 and see what happens. All right, so it's run. If I look in the workspace here, I have now found a q of 2.347. And I can save that into blist. So let's see what I have so far. So I have that first root, 0.937. The next smallest beta value I have found is 2.35. Now I can exit this loop and go back to the top of the for loop, and now k is 3, and I'm going to look for the third beta value. Well, same premise as before. I'm going to start searching for it a little bit higher than the second beta value and keep this iterative process up until I find what I am deeming a third unique beta value. Then one final time for the fourth beta value. So I'm going to run this whole thing here. Right, so it's completely run. If I look at this blist, it's now complete. I have all 4 of my values, and they should be unique, and they are. They're definitely distinct from each other. Again, I'm hoping I did not miss a beta value, and that's why I'm increasing the start point seemingly slowly or seemingly in small increments, but there is a possibility that I could have overshot a starting point and missed one of the betas. But I can confirm this with the book values, that these are the first 4 beta values for these boundary conditions. So finally, I want to convert these beta values to the natural frequencies. So keeping in mind this beta, what am I going to do with it? Well, I come down here, I'm going to take each of these beta values and square it and multiply it by c. And this goes to what we saw on the slides, the conversion from these betas, which are mathematically convenient, to the actual natural frequencies of the beam. So I take each beta, I square it, I multiply it by c. Here I have my definition of c. So remember, for the transverse beam, c was defined as the square root of ei over rho a. And this will then give me the first 4 natural frequencies. All right, so I have them printed out here. First 4 betas, and now the first 4 natural frequencies. So 444 radians per second is the lowest, all the way up to about 15,300 radians per second is the 4th natural frequency. So I have, in a little bit of a complex process, found the beta values that force the determinant of that A matrix to be equal to 0, which that was my goal. And then I can take those betas, convert them to natural frequencies, and these are with, I'm only printing out 3 digits of precision here, but to 3 digits of precision, the first 4 natural frequencies for the beam. So finally, I will transcribe them now with a little bit more detail. What are those natural frequencies? So we found that the lowest one was 444 radians per second. Then we have a 2781 with 4 digits of precision now. 7786 is our third, and 15,256. And these are all in radians per second. So this does answer that question. What are, well, in this case, I'm only looking for the first 4. I could have kept going in that loop, but 4 is going to be enough for this example. These are the first 4 natural frequencies of the beam in transverse loading.